Well, I'd like to wish everyone who's watching us today a good afternoon. This is one in a series of seminars that we broadcast live out over the internet. We do these periodically. This is our fourth one this year. My name's Dan Peruzzi, and my colleague Masha Stern and I will be talking to you today about some stereological applications that are useful for lung research. At this time, you probably want to adjust the volume on your speakers. I think my voice may be at a different volume than the test voice that you might have listened to. Also, while we are coming to you live today, we are also recording this presentation, and a link to that presentation, I believe, will be emailed to you at the end of this presentation. Okay, so what to expect from today's webinar. I'm going to start out and I'm going to give a broad overview of some stereological probes that are useful to use for lung research. So I'm going to be giving a quick explanations of these various probes that you can use to look for morphological characteristics that's useful to you in the lung. And when I'm done with that, my colleague Masha is going to take a more of a specific approach with one of these probes. Specifically, it's the physical fractionator modified to be used to count alveoli. If you want to come up with the number of air sacs in the lung, you can use this probe, and we are going to demonstrate how to do that in our software when I'm done giving a broad overview of all the probes that you can use. If you have questions that you think of during the presentation, please write them down in your question window, and we're going to pause to answer some of these questions during the webinar. If you think of a question later, you can always email it to the address you see on your screen, info@nvfbioscience.com. Okay, so first of all, what is design-based stereology? And what I've done is just put three definitions that I found from the literature. Definition 2 is taken from a book called Stereology for Statisticians, and definition 3 is taken from a book called Unbiased Stereology. These are great references for you for working with stereology in biological systems. The idea behind stereology is that we are going to throw down geometrical probes, virtual geometrical probes, into the tissue, and we're going to look at the way the characteristics that we're trying to find out about interact with these probes. For instance, if you want to find out the surface area of the alveoli in the lung, that's a surface area, so you can use a line probe. You can throw down virtual lines onto the tissue and record how many times those lines intersect with the surface area that you're trying to find out how big it is. And there's a formula for that, and the gut instinct behind the formula is that the more intersections you get, the more surface area there is there. So stereology is can be used for the geometrical properties of features in 3D space, and they can be quantified by throwing these random geometrical probes. For instance, if we're looking for length, we would throw a plane down there. If we're looking for lines, if we're looking for surface area, we would throw some lines down there. These geometrical probes are of various dimensions. They have to be random in orientation, and you record the way in which they intersect with the structures of interest. And we're going to look at some of these probes and the ones that are useful for lung research. So the question is, why use stereology? And I want to give an example that's taken from the lung literature to illustrate why it's important to use stereology. And this is taken from a paper by Hyde et al. From 2006, and he's talking about his they're talking about their 1983 study. And in that study, their goal was to find out, they wanted to compare the number of ciliated bronchiolar cells to the number of non-ciliated cells. And they took two ways to do this, a two-dimensional approach and a three-dimensional approach. And the two-dimensional approach would be on a par with a non-stereological approach. And to do that, if we look at this illustration, it's a block of tissue, and it has 6 physical sections that it's been cut into. And if you are not going to look at if you're not going to use a three-dimensional approach, then you're just going to be looking at the tops of each section and counting the profiles. And it turns out that the part of the ciliated cells that they were looking at was bigger than the non-ciliated cells. And so the profiles of the ciliated cells are more prevalent. When you cut up the tissue block, you see more cell fragments of the ciliated cells. And so you think that you have more ciliated cells, and what you really have is more ciliated cell fragments because the ciliated cells are bigger. And this is what happens when you use a two-dimensional approach. And they compared this to a three-dimensional approach and found a significant difference in the numbers of cells they counted. And their three-dimensional approach used special rules, followed special rules. And when we use stereology, we're going to follow these special rules so that we eliminate the bias before we even do the experiment. For instance, we want to eliminate the fact that big cells will be counted more than small cells. So this number estimate can't be done in two dimensions. You have to have at least two planes. And if you're using two thin physical planes, that's called the physical dissector or the physical fractionator. If you're using thick sections with many focal planes to compare the various planes and decide whether the cell is countable or not, there's a probe called the optical dissector and the optical fractionator that you can use. One of the special rules for these probes is to pick a unique point on the cell. For instance, we could use the top of the cell, and we can see that the cell top, unlike the whole cell, is not going to appear in more than one section. So when we use a 3D approach and we follow special rules and we use the physical fractionator or the optical fractionator, we will be counting the cells in a way that we won't overcount the cells. We won't bias ourselves. And so that is an illustration of why you want to use stereology. After you record all of the cells, after you actually do the probe and count all the cells, then there's two separate ways to come up with an estimate. And our program can do both of those ways. And I'm going to be talking about both ways to come up with the estimate of the total number of the feature that is there. Okay, so let's talk about designing your study. First of all, before you even get to our program, you want to think about, obviously, what is your scientific question, and then translate that into what type of data do I need to collect. And the big question may be, do I even need to use stereology? If you need to just show a qualitative difference and you can see it with your eye, you probably don't need to use stereology. But if you want to show small quantitative differences, or you want to get absolute numbers, then you should use stereology. It's an efficient and an unbiased way to get an estimate without counting everything that's there. You have to think about how are you going to see these cells or these fibers or these blood vessels or these alveoli or whatever you're trying to characterize. Will it be in bright field? Will it be fluorescence? Do we need to bring it down to the EM level? How will the histology work? You're going to need to be able to see these features under the microscope. We need to think about, so I'm going to talk about briefly about these different probes and the rules that have to be followed to eliminate bias, but you also want to think about how much sampling you're going to do, how many sections you're going to skip, how much sampling you're going to do on each section, and come up with a sampling scheme that's enough so that you get the precision you need, but not too much so that you're doing unnecessary work. And here is an example of a sampling scheme, a cascade sampling design. And in stereology, it's really important to section all the way through the organ. And that's why on the left side we see one of the lobes of the lung is sectioned all the way through. So we don't want to be looking at just one stereological section. One stereological section is biased. We want to systematically and randomly section through the whole organ. And this is just showing that as we zoom in from the gross level down to the EM level, whichever method you use to get the estimate, you want to be random and systematic at each level with your sampling. And if you can, you want to keep track of the volume fraction. In other words, what percentage of the tissue are you sampling? If you want to, you can employ the smooth fractionator, which means that you're going to line your sections up in order of size, and that may increase your efficiency. And this slide just gives me another chance to kind of hammer home the idea that we want to be sectioning all the way through the lung. or all the way through the region of interest. We don't want to look at just one section. Okay, so once you have your experimental question in mind and know what type of data you need to visualize and get the histology working, figure out the sampling scheme, now it's time to visit the different sections and actually do the probe. And this is a list of different types of data that's useful to lung researchers. Now, all of this data, there's applications, stereological applications, there's stereological probes that can be used to get this data either on thin sections or thick sections. And I'm not going to go into the details as I go through this data, which probe to use for which, but we can definitely help you out with that. Also, when you're estimating length or surface area, you need to worry about how your tissue is oriented. Either the probe or the tissue or some combination of those two things need to be oriented such that you're random in all three planes. That's called an isotropic situation. And there are probes that help you to various degrees to get this randomized situation, and I'm not going to go into the details of that as I go through this list, but we can help you think about which probe you use, not only for thin or thick sections, but which probe you need to use to make sure that your feature you're looking at or the probe is oriented randomly in all three dimensions in space. Okay, so volume might be something you're looking for. You can estimate, rather than tracing the volumes, you can estimate the volume, for instance, of the whole lung by using point counting and combining that with the Cavalieri probe. If you're looking for surface area, a lot of times the alveolar surface area or the endothelium surface area, those are really important data for the gas diffusion. If it's a surface area, we're going to use a line probe. Here's a couple different line probes in our program, Cycloids for SV, that will help you with the random orientation, or you could use a Weibull linear tests. These are line probes to probe for how much surface area is there. If you're looking for how many cells are there, here's two different probes you can use for thin or thick sections, optical fractionator or physical fractionator. My colleague Masha is going to show a demonstration of the physical fractionator, not to estimate the number of solid particles, but if you're looking for the number of air sacs or alveoli, there's some special things you need to do in order to identify the alveoli, and Masha is going to give an example of how the Stereo Investigator software can be used to estimate the number of alveoli, and that'll be after I'm done with this broad outlook. If you're looking for the size of cells, say the size of type 2 cells, rather than tracing the cells, you can use a probe called the nucleator, where you use a line to probe for the volume of those particles. You may be wondering about the percent of parenchyma in the lung, or, as is written down here, the percentage of lung fibrosis. Maybe there's lesions in the lung, and you're looking for the percentage of lesions. We can use point counting, which is riding on top of a fractionator, which allows us to be random and systematic, to get an estimate of the percentage of one type of tissue per another type of tissue in the lung. You may be wondering about the blood vessel length or the elastic fiber length. Here's a couple probes, Cycloids for LV or spaceballs, which can be used to estimate the length of strings, for instance, length of fibers. One type of data that's important to lung research is what is the thickness between where the oxygen is and the red blood cells. There's a probe called orthogonal intercepts that can be used to estimate a width. So the idea behind all these probes is you use a geometric virtual shape to probe for the feature that you're looking for, and you follow the special rules so that you don't come up with a biased estimate. For instance, we want to avoid the fact that big cells will be counted more than small cells when we're looking at cell number. Okay. Once you have done the probe, once you've recorded all the interactions of the virtual geometric shape with the characteristic that you're trying to, for instance, find the surface area of, then the program can figure out the estimate, and it can do it one of two ways. And the first way I want to talk about is called the NvVref method. And the way this works is the program comes up with a numerical density, and that's called NV. So if we're estimating the number of cells, after we mark all the cells in the virtual space that we restrict ourselves to counting in, the program will take that number of cells and divide it by the volume where you sampled. And that will give you a density of cells per volume sampled. So that'll be cells per micron cubed, for instance. And then you need to take the volume of the whole region, which you get by some other method, maybe through fluid displacement or maybe through point counting on the whole volume. So you multiply the numerical density, which is in this case number of cells per volume, by the total volume, and that'll give you an estimate of, for instance, the number of cells. Down here we show an example of how this could work for volume. If our reference volume is the whole lung volume, and then we section systematically and randomly through the whole lung, again, it's really important to go through the whole region, and then we look at each one of these sections and we can do point counting to see the ratio of the parenchymal volume, which is shown in red, to the airways and capillaries, the non-parenchymal volume, which is shown in green. That would be the NV, and we can multiply that by the reference volume to come up with an estimate of parenchymal volume. If we bring it down to a smaller scale, we could use the parenchyma as the reference volume to multiply by the ratio of the septal volume to the non-septal volume. In this level 4 illustration, rather than doing point countings to get the NV, we're putting lines down and marking where the lines intersect the surface area of the alveoli. And this would give us a numerical density of surface area per volume, and we could multiply that by the reference volume to come up with an estimate of the total surface area. Now there is a big flaw, there's a big drawback to this method, and that is, what if your reference volumes are being affected differentially by artifact? So what if your reference volume for your controls have shrunk more than for your experimental group? You're going to think the number of cells or the surface area has gone up per volume, when really what's happened is the volume has shrunk. So when you can, we highly recommend that you keep track of the volume fraction. In the lung literature, and here's a reference, they also recommend that if you can keep track of the volume fraction, you do it. So rather than the NvVref method where you're taking a density and multiplying it by a reference volume, the Fractionator method has you keep track of the volume fraction. So for instance, and here's the volume fraction at the right of this equation, if you sample 1/500th of the whole three-dimensional organ, you're going to take all of the cells that you counted in all of the virtual spaces. Here they are all lined up on one section. To the right, we can see the virtual spaces lined up on one section. You're going to take that and multiply it by the reciprocal of the volume fraction. In other words, we're going to extrapolate our estimate out, and that way we don't have to worry about reference volumes that are differentially shrinking due to artifact. So when you can, in the lung, keep track of the volume fraction and use the Fractionator instead of the NvVref method. Okay, let's take a look at some of that data and take a broad overview of how these probes work. What if you're looking for the volume of the lung? Or what if you're looking for the volume or the percentage of one type of tissue per another? For instance, parenchyma versus the bronchioles and vessels, or the percentage of alveoli, or you may be interested in the percentage of type 2 cells, or working down to the EM level, you may be interested in the percentage of lamella in the type 2 cells, which may give you an indication of how much surfactant is being made by those cells. Instead of tracing to get the volume, and to be very efficient, you can use stereology, and you'll use point counting along with the Cavalieri probe. The volume of the object is estimated by summing the areas that you mark on the regions of interest. I'm not going to give a complete demonstration of these probes like Masha is at the end for the connectivity assay. You can always call us up and we can help you with the probes. Or if you want to look at another webinar that's been done on point counting and Cavalieri, you can refer to that. It's shown in green at the bottom of this slide. So this is the way the point counting works. You section all the way through the region, systematically and randomly, and then you take the first section, here it's shown on the left. The program will put an array of points over the section, and you mark, in this case, a blue star over every vertex that you see over your region of interest. Each one of these points, and the point is the vertex of the plus sign, has an area associated with it. The program multiplies the number of blue stars by their area and then multiplies by the thickness to come up with an estimate of the volume. If you want to know an estimate of one type of tissue per another, in this case non-parenchymal tissue, you can use the point counting in a probe called the area fraction fractionator. So the point counting will ride on top of the fractionator. What you can see on the right illustration allows us to randomly and systematically visit different XY locations, and then when you get to those XY locations on your sections, you'll use a red triangle to mark one type of tissue, in this case airways and capillaries, non-parenchymal tissue, and a blue star to mark the parenchymal tissue, and then you can get an estimate of one type of tissue per another type of tissue. And that probe is called the area fraction fractionator and uses point counting. Okay, let's move on from volume to surface area and length. And unlike volume, for surface area and length, we need to worry about the orientation of the tissue. If you are probing for surface area, for instance, surface area of the alveoli, you can use various line probes. You have to make sure that some combination of your probe and your tissue gives you a randomness in 3 dimensions. So some of these probes will help you with that, like cycloids for SV. And if we look at the top illustration on the right, the red cycloid lines are probing for the surface area. So it's your job to mark every place where a red line intercepts a plane of the surface area of the alveoli. The more interceptions you get, the more surface area there is. In this probe, you also mark points down every time one of these little corners falls on the region that you're probing. So this Cycloids for SV probe will actually give you a surface area per volume estimate. If you think that your tissue is isotropic, or you arrange for the tissue to be isotropic, you can use straight lines instead of cycloids. And here's one example at the bottom, the Weibull linear test. Take-home message, we use a line to probe for a surface area, and we'll get an estimate of the total surface area of whatever you're looking at. If you're looking for length of objects, we can use planes to probe for the length. So rather than putting a cycloid line down, and this isn't illustrated here, but we would put a cycloid plane down, and you would mark, and that's called cycloids for LV, you would mark where these planes intersect the lines. If you can actually get thick tissue instead of thin tissue, you can use spaceballs. In this case, we use a sphere, and you mark where the blood vessels or fibers intersect the sphere, and that is an isotropic probe, so you don't need to worry about whether your tissue is isotropic. So take-home message on this is we have various probes to use to probe for surface area. We use lines, and we implement other people's probes in our software. And to probe for length, we put planes down. Okay, let's move on. We've talked about estimating volume, we've talked about estimating length and estimating surface area. Now let's talk about estimating the number of particles that are there. If you have thin sections, if you can only get thin sections, use something called the physical fractionator. And remember, we can only do number estimates in 3 dimensions, so we need 2 physical sections. We compare the reference to the lookup section and decide whether to count the cell. If we can get thick sections, if you can get thick sections through your lungs, use thick sections instead and do the optical fractionator. It's easier than the physical fractionator. You're going to be focusing through and deciding whether to count the cells or not. And something that's going to help you make that decision is called the Disector. This is the virtual space where we restrict ourselves to counting. On the left is an example of 3 nuclei that are marked in the lung. So in this case, we marked 3 cells in this Disector. This dissector and other rules allow you to follow these special rules for this probe so that you, for instance, we won't count bigger cells more than smaller cells, and we won't overcount cells. We're going to take a lot of pain to count only the cells that belong in this dissector, and therefore we won't be overcounting the cells. Okay, if you want to get an estimate of the volume of a solid particle, you can use a probe called the nucleator rather than tracing the cell. We focus down through the cell and put a mark, in this case it's a white star, and we put it on a random point in the cell. We can use the nucleolus, that's why it's called the nucleator. And then the program shoots out these yellow rays, and then we take these green triangles. On the right they're green triangles, on the left they're red X's. And we mark where these rays intersect the periphery of the cell. It's put through a formula, and we get an estimate of the volume of the cell. This can also be used, for instance, if you want to look at the thickness of a blood vessel wall. We can implement what's called a donut nucleator, where you go around and mark where the rays intersect the inner wall of the blood vessel, and then we allow you to go around and put marks where the rays intersect the outer wall of the blood vessel. So you can use this nucleator to get nested volumes if you need to. Okay, so I'm just going to kind of say in summary for this broad overview of the different probes that you can use to get useful data in the lung, that after you come up with your experimental question and then translate that into what type of data do I need to get, and then figure out the histology where you're going to be able to see those cells or those fibers or those air sacs, and then think about your think about what probe you need to use, how to follow the rules for that probe so you won't be biased, and also think about how much sampling you need to do because we need to go all the way through the organ, and we can help you think about these things. And then you actually do the histology and do the probe. In other words, mark the interactions of the geometrical probe with the feature that you're trying to characterize. When you're done with that, our program will give you the results. It will give you the estimate, either through the NvVref method or the Fractionator method. It will also give you any CEs, which are formulas that try to gauge how good of a job you did with your sampling. We'll also show you the references where this information came from. So thanks a lot for your attention on this first part of the talk, where I just gave a broad overview of some of these probes. Now I'd like to introduce my colleague, Masha, who's going to go ahead and give a more specific, in-depth example of how to estimate the number of alveoli. Before we do that, I'd like to take a pause and see if we have any questions about my part. Okay, one question I'm getting is how many minimum lung sections per lung are required for the stereological evaluations? Now that is something that we're not going to be able to answer directly with a number, but what we're going to be able to do is work with you and look at your system. You're going to be an expert in your system, or what we really need to figure out is what type of precision do you need. And there's three ways that come to mind to think about this. You can search the literature, for instance, and if you see that someone has already done this and they write up good reasons for why they picked their section interval, why they picked how many sections to use, that's a good place for you to start. Another point is you need to be an expert in your region. So if there's some clump of cells in there that you never want to miss, don't make your interval so far apart that you might miss that clump of cells. There's also an excellent paper from 2005 by Lutz Slomianka and Mark West, they say that if you're really new to a region and want to get a handle on how many sections to skip and also how close together to place your virtual spaces, you can oversample the data and then back off on the sampling to kind of find a sweet spot where you're doing enough sampling so you get the precision you need, so your control is different from your experiment, but you're not doing too much sampling where you're turning a 2-month experiment into a 6-month experiment. And so let's continue that conversation. You know, get in touch with me, get in touch with us. We can help you not only follow the rules for these probes to eliminate bias, but also we can help you think about how much sampling to do, and it's really going to depend on what precision you need and how homogeneous or heterogeneous your feature is that you're looking for. Okay, that's all the questions we have time for. If you have more questions, send them in. Now I'd like to turn this over to Masha, who's going to give a specific example of how to count alveoli.
Thank you, Dan. Hello, everybody. So I'm going to go through and discuss how to count alveoli in a lung. We'll first discuss a little bit of the theory, and then we'll move on to practical demonstration as well. So when we count alveoli, the trick in counting those is the fact that they're not isolated particles. They really have openings. They open up into the ducts, and everything's interconnected, so it's really hard to count them in regular dissectors in ordinary way. So what was developed was an application of physical fractionator that Dan mentioned earlier that I'll be able to demonstrate to actually be able to count alveoli. So if you look on a screen and you look at the picture A on the left-hand side, you will see SEM photo of the alveoli opening, and you will see that we can see the opening where it's not connecting. Well, of course, we have to somehow define when the alveoli is created, and that's where you can see the two images that are in figure B on the right-hand side of the screen. And you will notice that you have two different counting frames, two different dissectors. And in dissector on the left, you can see with the arrows pointing where the alveolar opening is opened up. And you can see where there is a bridge or a unique point that we can count is created on the right-hand side of the screen. And that's what we're going to count. So we're making an assumption that when the alveoli is created, that's where we have a closed-in bridge, and that's what we're going to count. And that's how we're going to translate it into 2D. The way it's actually done in the software, we'll go through the steps here, and we'll actually do the demonstration in a minute, is we'll go through and we'll set up our reference and look up sections. As Dan was saying earlier, we need physical sections. What that means is you will cut two adjacent sections, section 1 and section 2 right after. Then you can skip certain amount of space. Then you again cut section 1 and section 2, and you proceed like this through the whole lung. And addressing again the question that was we heard earlier about the minimum number of sections, you have to remember you're trying to give the whole lung equal opportunity to be sampled. And depending on what you're looking for and how different the result may be, you might have to sample more frequently or less frequently. So again, there's going to be a pilot study you will do to figure out what actually your sampling periodicity should be. You could do this on working from the tissue section on the microscope. You also could, what we'll do in our example here, we'll actually previously acquired some images that we'll use to be able to outline our region and actually do counting from those. But you have two options within the software to do it live or to do it from the acquired images. And what we'll do is we'll set up our dissector or the counting frame, and I'll show you how to do that, as well as we'll set up the fractionator or the grid size, where we'll not be sampling the entire section, we'll be sampling certain subfraction of the section to get it more efficient. And the way we'll mark the bridges is we'll be able to line up our reference and the lookup section. And that's where Dan was talking about that the reason why optical fractionator usually is preferred is you don't have this alignment step that will take a very long time. But in case of alveoli, we do have to use physical fractionator because we need to compare two physical sections. So we'll line them up, and it is pretty easy to do. I'll show you how to do it in software. Once those are lined up, we'll go in and look at two different sections. We'll look at our reference and lookup. And what we'll see is that if you look at the top left part of the counting frame on a screen, we don't have anything on the reference section, but then on the lookup, we'll have bridges connecting. And that's what we're going to count. So you can see I'll switch back and forth again. And of course, when we do stereology, we're seeing random events, and we may or may not see any bridges. Hopefully, we'll get some when we actually go through with it. But I want you to make sure you had opportunity to see where there was no bridges and when we actually got bridges to connect. And at this point, we'll go ahead and proceed to the software. What we'll do is we'll go to probes and we'll select the appropriate probe for us to work with. You'll notice it's a pretty long list, so there's a variety of probes we can choose, and there's, some of them Dan has discussed, and we do have very many of these, which probably will take us quite a few weeks to go over. But we'll go in and start connectivity assay. We'll start the new subject. At this point, we have an opportunity to write down the name of the person who's doing the work, perhaps any notes on this particular subject we're working with or this animal. If we had parameters saved from previous experiment, we could upload these and work with them. We'll actually do ours from scratch. We can put in the distance between the pairs of the sections that we have. We're also going to put in the reference and lookup position, and that's really the thickness of the sections that we have. So we start from 0 microns and we go to 5 microns for lookup, and lookup is going to be 5 to 10. We can also choose the image source. We could go from live video or from the image file, which is what we're going to use here. I can upload our reference images that we collected before, and I will also upload our lookup. And we'll proceed to the next step. The next step tells me to set up the microscope to low magnification. Of course, right now I'm pretty zoomed in into this image, so I'm going to go ahead and zoom out. And on the right-hand side, I can actually use our macro view, which is a special tool we have that shows you everything you have everything you have to work with. And at this point, I could go ahead and go to the next step to be able to outline my region of interest. And at this point, I could outline multiple regions of interest or just one. We'll go ahead and do one for the demonstration purposes. So once we're done, we're going to close the counter. And now we have defined region of interest we're interested in working with. We'll proceed to the next step where we go back to final magnification. We're using 10x magnification here because these were monkey preparations, therefore it's pretty large scale. So we'll proceed to the next step. At this point, I could set up our counting frame. I know it's a little bit hard to see for you this step perhaps, but you'll be able to see it easily in the future steps. We can manually set up the size. As Dan was mentioning, this is the dissector, and the point of using dissector is we want to count objects once and only once. You know, despite of are we counting bridges, connections, cell particles, anything we're doing. The way you want to generally set up the dissector is you want to limit user error. So you want to make it small enough where you only count few objects in it, and you also want to be able to count efficiently. And you will notice as we proceed, we'll all be looking at different parts of the same dissector, which is why it's so small, is that we want to make sure we're not missing any points to count. So we'll proceed to next step. This is where we can set up our grid. What the grid tells us is we can go in and say we want to see approximate number of sites. This way we can see what roughly the distribution is going to be. What that implies is that we're trying to do systematic random sampling. The systematic part is the size of our dissector and the spacing between the dissectors. The random part is the actual placement of the dissectors on a screen. So every time I click on display changes, the location of the grids on a screen changes. We'll do fewer counting frames for the practice sake, so we don't spend too much time on this. So we should see anywhere between 2 to 5 frames or so per structure. So we'll proceed to the next step. At this point, we could go ahead and save the parameters if we wanted, or if we don't save them at this step, they're actually always saved within the file, so we can save these parameters at any point after we're done or while we're working. So the next step is to acquire alignment images. I'm going to go ahead and gather the reference images. And if you look on the right-hand side in the macro view, you're going to see how the frame is moving across the structure and actually collecting all the images we're going to work with. So we'll proceed to next step, and at this point we could match our tissue sections. I'm going to go ahead and zoom out again, and you will see that where our previous tracing was, we need to line this up now with the new image or new section we're going to look at. You can line things up using multiple points. You can do 2 points, 3 points, or as many points as you like for alignment. I can select 3, for instance, and for aligning and tracing, I could say this point on the structure should be lining up with this on the image. And I'll do the same for 2 more points. And once it lines up, if I'm not happy with how it lined up, I can keep lining it up and tweaking it a little bit at a time until I get it just right. In this case, it looks pretty good, so I can stop here. I'm going to go ahead to the next step. And at the next step, we can actually proceed with counting. Right now, the software is loading all the images in that we gathered. And right now, we have an option of going to our probe run here. I can go ahead and start marking. And you will now see that I have an outline of 2 structures here. So I can go in and actually manually move the image, reference, and lookup until they line up pretty well. Once they line up, I could use different keys, and there's explanation for different keys on the left-hand side to rotate the image so that I can line it up the best, because remember, we're looking at two different sections, so they're not going to be lined up perfectly, and one of them may look a little more stretched out than the other because there are two different physical sections. Once we line it up the best possible way that we think we could do it, I can go ahead and click on the left-hand side to begin placing markers, and I'm going to start counting bridges. And we have a couple of ways to do this. One of them, we can change the transparency of the images, so we can look at the overlay. And another option, you can actually switch between the two images, which is often what I prefer to do. And sometimes you'll need one method versus the other, or both. So let's switch in back and forth a little bit. And for instance, you can see over here on the right-hand side at the very top of the counting frame, we're looking at lookup, and then we're looking at reference. Over here, you can see that outside of the dissector, we do have a bridge connecting. That is, however, happening outside of my dissector, so I will not count it because it needs to be inside of my dissector. But let's see over here. So over here, we can see that we had no connection. You'll see where my mouse is over here, there's empty spot, and there's empty spot on the other side of this little structure. And if I go to my reference, now I have these two connect. That means I can mark two bridges right here. Let's go through, and as I said, we probably all are looking at a different part of the system right now, but part of it is, that's why the dissector is pretty small, so we don't miss anything. So you want to go through and see if there is any other bridges to count. So again, this is the reference, that's the lookup, that's the reference. So we'll see. Here, actually, we're going to count in one direction. We're counting from lookup to reference. So actually, in here, we're seeing less bridges from lookup to reference. So we're not going to count those. We're going to stop here. So that's it for this counting frame. So we'll go to the next dissector. And again, you're going to go through and try to line things up the best way you can. We again go to begin placing markers. And we can again switch back and forth. And now we can see over here in the center, we didn't have this connecting, but here we do. So we put at least one bridge. And there's actually more. We had this one structure that moved through. And actually, you can see this structure over here on the left-hand side has become larger. So this bridge actually was not needed to be counted. So I can easily erase that. And I can double check again. And we'll see, but we do have a connection actually over here a little bit lower. So that's one bridge for us to count. Then also over here on the right-hand side, you will see there is no bridge here, but there is bridge on the reference. So we'll go ahead and count that one. And also on the bottom, you will see that on lookup, there is no connection over here at the very bottom of the screen. But there is a connection here, but you will see that that bridge actually is going over the red line, which is why I'm not going to mark it, because we can't count anything that is touching or crossing forbidden line, which is the red line on the screen. So let's go in here, line up our next piece of tissue here. And we'll go ahead and begin placing markers again. And again, this is our counting frame. And we have no bridge over here, but we do have a bridge in the next one, so we'll count that. And the same thing in the bottom, there is no bridge over here, but there is a bridge in the next one, so we'll count that. And I also should point out, you see the boundary line is pretty thick red line on the screen. We actually could easily change it to look very thin. So it's just a function in software. I have it pretty thick so you could see it easily for your presentation, but normally it would be very thin line that will not be in the way of the image. And now I'm going to go line this up again. Again, once we're done, we're going to put the new counting frame on. We'll switch back and forth. Looks like there is no new bridges here, so we'll proceed to the next frame. And let's go in here and look again. So we have over here, look up, there is no bridge, but there is a bridge on the next slide over. There is another bridge here. And I think this is it for us for bridges on this dissector. We'll finally go to the last one, and it looks like we're not going to see very much at this very bottom here, but we'll line it up. And you can see there's actually nothing here. See, you can also see that I can't really see behind this red line here really well. So what I'll do is I will shut off the thickness of the line, hide the line altogether. And let's change the transparency so it's not under my way as much. But we can see that we had a bridge and the lookup, but no bridge at reference. And again, we're only counting from lookup to reference, so we'll not be counting this one right now. So I will go ahead and proceed to the next site. So once we're done, the software will ask you to save the file, and then you have an option to go ahead and add a new pair of sections and proceeding to count. And of course, normally you will have more than just one pair. You'll have many more. In this example, we're only using one just to not take up too much of your time. So we'll go to the next step, and we can look at the results. For our results, we do list the parameters for you, so you have that available to you. We also give you the actual estimation with the volume and NV. We give you the equation, and we also give you explanation to the equation and where it came from. So when you're ready to publish the data, you should have a reference to go with the equation you need to use. We'll also give you multiple reference volume results. We give you a planimetric result based on your actual outline, as well as the Cavalieri result that is programmed into the software, so we get that information as well. So you have two different volumes, volume measurements, and we can export our data to Excel. So I'm going to be done with the software. Now I'm going to switch back to our presentation. And this is just an important point. You have to be very careful when you publish the results. You want to make sure you're very good at putting the proper parameters to report. You will notice this when you read other people's papers. It's fairly painful to be able to do the data properly or work properly when they don't give you enough information on what they've done. So we all try to do a better job with that. But for instance, for connectivity assay using NvVref, which is what we just did, you want to put properly histology details. Of course, you want to tell your colleagues how you've processed the tissue, how you define the region of interest. You want to use the proper probe, and of course, report the probe you've used. You will need to report which magnification you've used, what was the spacing between the sections, therefore section thickness, and dissector height will be important. In our case, it's section thickness as well. What was periodicity, so how much space you skipped between the section pairs. We'll need the dissector area, the number of dissectors, volume, and number of bridges that you've counted, as well as, of course, the final result to go with it. And that completes my part of the presentations, and we do have time for questions now, and we do have one question which came from somebody asking that could we use the program without the microscope because someone has the TEM. So you would want to use the EM images to do the data. And actually, what we just used in our software, we actually had the images that we previously acquired that we've used. So you can use the program with the microscope. So you would have motorized stage, you would have the slide on, and you could do work that way. But if you just have images to work from, you could do that as well, and you can use that just as a simple workstation system. So you can certainly do it both ways. And I think that is it for questions we got today. So this will be completing our webinar. Please make sure to send us more questions as they come up. You can always email us at info@NBFBioscience. You can visit our website. That's where we're going to have the published webinar later on, and I believe you'll receive email with the link to it as well. You can visit NBF Labs, which is the company within NBF that actually does